Alright, I would like to start off by looking at how to go from a logic function to derive a CMOS circuit that we can then use in our layout. And to start off with, we have a simple logic function here, y is equal to a or b, c. The canonicalization is always going to be y is equal to some function of our variables, in this case a, b, and c, with a single negation over the top of it. And that's for the CMOS functionality. So to do that, what I can do is introduce a double negation around the original function, and that doesn't change the truth value of anything. And now what I can do is distribute that negation into the function. So this becomes not a and not the quantity b and c. And the next thing I want to do is distribute that in one step further. So this becomes not a and not b or not c. And so this now is a canonicalized version of the formula that we're working with. One of the things I always find helpful is to write down the following little table. And the table just kind of helps me remember the order of the transistors. And so we're going to have our p-type and our n-type MOSFETs, and we're going to have an and an or. And I know that the first corner of this is always parallel. So the variables that are ANDed together, those transistors will be in parallel on the p-type, and those that are ORed together will be sequential, and then the n-type is just flipped. Alright, I'll use this just as a way to trigger my memory. So now the next thing I can do is I can derive the transistors. And so I'm only going to focus on the inside part of this, and we're going to have one term that is the not A, and another term that is the not B or not C, and those two terms are ANDed together, and so that tells me that I'm going to end up with some parallel transistors. So I'm going to have my VDD, and I'm going to have a P transistor, a PMOS, that is my not A, and then I'm going to have, because they're ORed, I'm going to have the two PMOS transistors in series. That correspond to not B and not C. And then I get my output function, which is going to be our Y, and these guys are just connected to it. To do the n-type, we're basically going to do the same deal, only I see that in the n-type, the AND means that they're going to be in series. So I'm going to have my N transistor for not A, and then I'm going to have, and I see that the OR of B and C is in parallel. Not B and not C, and these guys are all going to be connected to the ground plane. So that is the transistor schematic for the circuit that this function describes. So what I'm saying is this is equal to that. So now the next thing we've got to do is try to figure out how this gets us to a stick figure. And the typical technique that we can use for this is to derive the Eulerian graph. And to do that, we're going to take each of the nodes from here. And so there's a node up here, and there's going to be a node here. There's a node in between, and basically I'm looking for the points that are between transistors. So there's a node here, there's a node here, and then there's one node here. And then I can also use and derive the edges, and they're going to be labeled based on the gate names. So the Eulerian graph of this picture over here, if I have the p-type, and I have my node here, or this is the p part, p network. I have a node for v, and I have a node for y. And this single edge corresponds to, I'm just going to call it not A. And I have a pair of nodes over here, one corresponding to not B and the other one corresponding to not C. In the end part of the network, I have Y at the top, and I have a node going down here, and this would be my not A, and then I have a parallel set of nodes, or sorry, parallel set of edges going here to not B and not C, and then that would be my ground. So these two are the Eulerian graph interpretations. They have the same structure as this graph over here. So again, we're looking for the nodes, and we're looking for the edges that connect them. So we're going to derive now the Eulerian path that corresponds to both of these. And what we should see is that we can get to the same path through the graph for the P and the N networks. I can go through a node more than once, but I can only follow an edge once. So in this case, we could start up here at V, and I could travel on the not A network, on the not A node edge, to get to Y. And then I can travel up to here to get to across the not C edge to get to that node, and I can complete my journey, my path, by going over the not B node. So essentially I get the not A, not C, not B. And what I want to verify, and there may be others, for example, we could also do not B, not C, not A. We could even do not A, not B, not C. I don't know that there's any other combinations. Oh, not C, B, not A. Any combination that is valid, right? So not C, not B, not A, not C, not A, not B. Let's just stick with this guy. So I want to make sure that I can use this down here, that the paths both have to be compatible. So I can do not A, and then I can do the not C, and then we can come back around and finish off with the not B. So I can do the not A, not C, and not B. So those are both valid paths. And so what this does is the path gives me the order of the gates in the stick figure that we're going to draw. So with that in mind, we can clear this, and let's do the stick figure. Okay, so if we're going to do the stick figure, we can start off and draw our VDD and our ground nets. And I know I've got 3 variables, and so I'm going to end up with 3 gates. So we know this guy is going to be not A, this guy is going to be not C, and this guy is going to correspond to not B. So now, looking at the stick figure, I have the order of the gates. Now I can also look over here at the organization of the p-type, p part of the network. And what I see, for example, is that the sources of B, not B, and not A are tied together. And the drain of A is tied together with the drain of not C. And so, for example, we could come in here and choose to connect the drains of not A and not C. Alright, so this, what makes this the source and this the drain, it just depends on how they're energized. For the p-type, the source is going to have a higher potential than the drain. For the n-type, the drain has a higher potential than the source. So the fact that these two are tied together means that they are both going to correspond to the drain of their respective transistor. So I'm just going to label those. That means this must be the source for either of those two. We also see over here that we have B, and the source of B is going to be connected up to VDD. And the drain of B is connected to the source of C. So I don't need to have another line here. I can just tie those together. And we're going to see later on that when we have those things together, we can fold transistors together. These two that are folded together are also going to be connected to the output. So there's Y. We can now do the same kind of deal. We have down here the source of B and the source of C are tied together. So right in between C and B, we can tie that together, and that's going to become the connection off to ground. And that makes this the source of C, and that makes this the source of B, which makes this the drain and this the drain. We can also then look at not A and see that not A, the source of A is connected there, and so those can be tied together. And the drain of A is connected to our output function, like so. So that takes care of that right there. This guy is taken care of right there, and those two are taken care of right there. And the other thing we've got to do is have the drain of B also connected to the source of A. And so that takes care of that guy. So this stick figure is isomorphic with this part of the network. We can also check off here, we have A, the drain of A. Oh, look, I missed that. So the drain of A, sorry, the source of A is connected up to VDD. And so that takes care of that. The drain of A is connected to Y. So there it is. We have the source of B is connected to VDD. We have the drain of B is connected to the source of C. And we have the drain of C is connected to the output function Y. And that's it. So there's our stick figure for this logic function. So we just derived the stick figure for our logic function, and so now what I want to do is I want to convert that to a layout. And to do that first, what I'm going to do is I'm going to make a new cell. So in the layout, I'm going to create an instance of our cell, and I'm going to start off by putting it here at 0, 0. And then the next cell I'm going to put so that it sits right on top of and is aligned over the other part and one more time, and that's going to give me my 3 logic gates, 1, 2, 3, with my 4 sets of taps. I need to make sure that the width of this is going to be on that 2.4 micron boundary, and so I'm just going to measure from the origin over to here, and I see that it's 9.6, and if I use kcalc I can do 9.6 divided by 2.4, and sure enough it's right on one of the boundary lines. So next what I can do is I can draw in the, well, first of all, we should also make sure that Virtuoso is okay with what we've just done here. So I'll do a verify DRC. Let me move the output here into the window. I'll do a verify DRC, and so far Virtuoso is perfectly fine with this overlay. So now I can come in and create the poly rectangles, and one thing we might want to do to make things a little bit easier is to measure from here down to here to be 23.1 microns. And I know how wide the poly is always going to be. So if I create the rectangle, and the rectangle I specify the size to be 0.6 and 23.1 for the height. Then we can kind of center it. Center 1, 2, and 3 gates. Like so. So what I'm going to do is I'm going to grab metal 1, and I'm going to turn on smart snapping and connect A to VDD. And if you remember, the other guy here was also connected to VDD. Well, sorry, once current is flowing from here through this channel into here, it's also going to be able to flow from here into wherever else it's going to go. And that's a good point. Where else it's going to go is it's going to go down from this tap here to this tap here, based on the way that we've designed our stick figure layout. Metal 1 is supposed to be used for horizontal layers, and metal 2 is used for vertical layers. And with that in mind, what I'm going to do is I am going to create a via that's the M1, M2, and M1, M2, M1, M2, and we're going to put 4 of them, in a row. And we're going to put them on top of one another, and I'm going to go metal 2 and smart snap, and we're going to bring this down something like that. I'm going to come up my 1.2 millimeters, which is the size of a via, and I'm going to create another M1, M2, but this time it's just going to be a singleton. And this is going to allow me to route horizontally. I'm going to need another M1, M2. Stacked on top of that. And then we're going to bring that up here and come down 1.2. And now I'm ready to put another M1, M2 via. Again, a singleton here. And we're going to route that on metal 1. Okay, so we'll do the easy one first. This one goes off to ground. In this case, this one is so small. I'm not sure that it's really worth using a whole metal 1. I'm sorry, I'm not sure that it's worth using a via up and then a via down. It all depends. We'll have to do a DRC here, verify DRC, and this might be too close. That is too close. So now we'll move this up a little bit, which means we need to move this up a little bit. Okay, so at this point we have all of the connections made from our stick figure. The only thing we need to do is put in the pins, and if you remember, this was our output function, and then the other 3 pins would be our 3 inputs on the gates. So just like I did before, I have to go and put on those tracks. And now I can choose where I put my pins. And so we're going to run into a little bit of a challenge because I can't put a pin here. It'll be too close to the adjacent poly. So what I can do is I can do our M1 poly here, and that'll be fine. And I can easily put another M1 poly here. But I can't put an M1 poly here, it's too close. But what I can do is put an M1 poly right there. Put it right on top, and we'll do a verify DRC. And it says, hey, those two are floating, they're not really connected. So let's go ahead and connect those. So we're going to connect poly to poly and poly to poly, and we'll verify our DRC, and no errors. So now what I can do is I can label these 3 as my pins. If we pay careful attention, we'll see here that I don't have my output function on a boundary. And I like to try to keep these pins all in the same level. So I'm going to go ahead and create a rectangle on metal 1. And we're just going to extend it up the 1.2. And now what I can do is I'll create a pin. We're going to have our AN, BN, and CN on input. So that corresponds to AN. BN was over here, and CN was over here, and we're going to have another pin which would be our Y on output. And we'll do a verify DRC. No errors, so we'll save. I'll do my extract, and then we'll do our verify LVS, and we'll change this to foo, and we'll run, and hopefully the netlist will match. Oh, I don't have VDD or ground. So we'll create a pin for VDD and ground. Okay, now I can do my pin. It's going to be GMD in and out, and we're going to be right there. And okay, so now that the netlist match, we can do our build analog. And we've successfully gone from a CMOS logic function of some arbitrary design to a circuit layout.